Okay.
Okay, thank you very much. So I am going to present some basic mathematical facts about quantum field theory and some of issues that we are dealing with regarding the Navier-Stokes equations and the gauge theories. So let us start. So first, let's start in the physical level. What is a QFT? It is the framework that combines special relativity and quantum mechanics. In the high energy regime, that is like very fast moving particles. Particles may be created or annihilated in various physical processes, such as like electron and positron can be pair annihilated and create photons. Thus, individual particles such as electrons must be replaced by corresponding operators, which are distributed throughout the space-time and create or annihilate these particles. Such a collection of operators are called a quantum field. I just said that our space-time, the operators are distributed throughout the space-time. So we have to model the space-time first. Our space-time is modeled as R4 equipped with the Minkowski metric defined as diagonal matrix -1, 1, 1, 1 with respect to standard basis. Physicists prefer to work with a specific basis and the components of the inner product. So they present the instead of some abstract pseudo-Riemannian metric, they present this specific matrix as the metric. Also, Greek letters such as mu and nu are the space-time indices that by convention have the values 0, 1, 2, 3. So -1 it corresponds to the value 0, and the space and the spatial indices 1 to 3 corresponds to the spatial metric 1, 2, 3. And we write an arbitrary component of eta as eta mu nu. Note that mu nu are superscripts. The inverse of eta is equal to itself. Its components are denoted as eta mu nu, where mu nu are the subscripts. Since we have fixed the metric, covariant and contravariant tensors may be canonically transformed to one another. For example, the components of some the components of some x contained in R4 may be written as x superscript mu or x subscript mu with the relation given as this. In fact, this x mu it belongs to R4, and this x mu with subscript mu belongs to the dual of R4, which is equal to R4 in fact, and isomorphic to R4 in fact. So they are related by the metric, and metric canonically identifies them. And here comes the very important convention of the quantum field theory. That is the Einstein summation convention.
Wait, can I have a question?
Yes.
Is a geometric point, its coordinates should be thought of as lower indices or upper indices?
What do you mean by geometric coordinates?
Geometric point.
Point.
Space, time.
Point itself can be either belong to the either belong to the R4 or each dual because they are isomorphic.
Well, yeah, but which one is which? Upper and lower. I mean, you have points and then you have linear functions on R4, and there has to be a convention. You're talking about particles moving around, and then you talk about linear functions or observables. These are different conceptual entities. And so
The lower index
even
is
though they're isomorphic, you have two indices, upper and lower, which is which? The question makes sense.
the upper index is the point and the lower index is the linear functional.
Okay.
Oh, yes. Actually, I have not been really discriminating those sort of issues, but yes, it seems so. So they are related by this formula, and we just get rid of this summation symbol and write as this. From now on, we will always omit the summation symbol if there is one upper index and one lower index, which means that these indices are contracted. We say that a vector x is space-like or light-like or time-like vector if this inner product x mu nu is negative, 0, or positive. This is the causal structure of Minkowski space-time. A space-like vector, it cannot be a space-like vector has the physical meaning that it cannot be linked to the origin by light, by anything that is slower than light, anything that is slower or that is of equal speed than light. And light-like means that the x can be connected to the origin only by light, and time-like means that x can be linked to the origin by something that is slower than some media that is slower than light. And so if two objects are space-like separated, meaning that their separation is a vector that is that is space-like, then they are not causally connected, because in special relativity, everything is assumed to be the transmission of information is assumed to be slower or equal to the speed of light. So the basic assumption of special relativity is that all laws of physics must be invariant under the Poincare group, which is also called the inhomogeneous Lorentz group. QFT aims to incorporate this principle into quantum mechanics. However, the Poincare group contains discontinuous symmetry operations, which are the parity and time invergence. You can note this by that the Poincare group consists of four disconnected components, and this parity and time invergence may cause subtlety for quantum theories. This is where is illustrated in the classic book by Arthur Weitman, which is called the PCT, Spin and Statistics and all that. So for now, we only adopt the restricted Poincare group as the symmetry group of QFT. So for the restricted Poincare group, we means that there's no time inversion, there's no parity inversion. We only think of proper and orthochronous Lorentz transformations. So what exactly, yes?
What is parity inversion?
Parity inversion means that the direction of space is inverted, meaning that the orientation of the space inverted. A
Okay.
time invert.
The time inversion.
Yes. And time inversion means that the direction of time is inverted. And these are discontinuous symmetry operations. These are known to be discontinuous symmetry operations. So shall I continue?
Raphael has a question in the chat.
Hey, when you say invariant under the group, what exactly is invariant? Are you saying the solutions to certain differential equations are the same? I'm not quite sure what it means for the laws of physics.
Everything to come.
Oh yes. This is all laws of physics must be invariant under the Poincare group. This is yes. This must come as some kind. This must be some not very exact for mathematicians, but it means that yes, the solution of equations of motion must transform exactly as the equation of motion itself under the Poincare group. That will explain what you mean, what you were questioning about. So basically, what physicists wants to say about this is that regardless of the coordinate with which you're observing a phenomenon, you get the same result. You get the same result and same judgment, regardless of this coordinate. That is the law. That is the invariance of the law of physics under the Poincare group. So what exactly is a quantum field? As stated above, it is a collection of operators on the space-time. However, by the uncertainty principle of quantum mechanics, it cannot be defined on each point of the space-time, because the uncertainty principle says that if you're able to exactly specify a point, a space or a time, then the energy or momentum must be infinite. So in other words, a quantum field is a operator valued temporal distribution. Moreover, it must have a appropriate transformation property under the restricted Poincare group. The causal structure are to be considered as well. All these considerations led to what is called axiomatic QFT, which aims to build QFT upon a set of rigorous axioms. Such a discipline was launched in 60s by Arthur Strong Whiteman, noting that quantum field theory was a big success in calculations and predictions, but was not well established in mathematical definitions. So here comes the axioms, axiomatic formulation of QFT. These axioms are called, I just briefly present the axioms because it is very hard. They are very intricate and many details are involved. So these are the full details can be found in the book of Forland I just referred, or another book, Local Quantum Physics by Rudolf Haag. And so these are the Whiteman axioms, and let's briefly state them. First, a quantum field theory must satisfy these axioms in order to be a reasonable theory. First, there exists a set of operator valued temporal distributions, phi1 through phi(n), whose values are defined on a common dense subspace D of some separable Hilbert space H. Also, there exists a unitary representation U of the restricted Poincare group on H and a non-unitary representation S on Cn. Third, there exists a unit vector omega, unique of the phase vector that is invariant under the unitary representation U. This unit vector omega is called the vacuum. And phi(n)s satisfy a transformation law given as this. Here, in fact, U and S depend on the spin of the phase. And if X and Y in R4 are such that X minus Y is a separate spacelike vector, then all phi(m) and phi(n) commute or anti-commute as operators. Okay, so they commute if any one of phi(n) or phi(m) is a bosonic operator, meaning that they are integer spin operators, or they are anti-commute if both of them are fermionic operators, meaning that they are half integer spins. And the spins are as you may well know, these spins are the classification of the representation of the Lorentz group. And there is a little bit of digression, which is that our Minkowski quantum field theory is equivalent with the Euclidean theory. The Euclidean metric is much easier to work with than the Minkowski metric eta, because the Euclidean metric is positive definite. Thus, in practice, construction of a non-trivial field theory starts in the Euclidean space R4, and then we return to the Minkowski space-time. This amounts to introducing the imaginary time, tau, which is called the weak rotation, because if we think of only time and think of the complex plane, we rotate the time coordinate from the real line to the imaginary line. This is called so is the name weak rotation, and this raises the issue of analytic continuation for QFT with respect to the time coordinate. A famous paper published by Osterwalder and Schroeder in 1973 presents the conditions under which a Euclidean field theory yields an ordinary quantum field theory. Those conditions are temporaleness, Euclidean covariance, reflection positivity, symmetry, and cluster decomposition property. These all have very detailed analysis, and there are many theorems that are related to these axioms. However, this is not the main line of this talk, so we will return to the Minkowski space-time.
Thank you. That was a nice summary.
Thank you.
You should mention that the Navier-Stokes comes from the Euclidean formulation.
Yes, Navier-Stokes equation actually comes from the Euclidean formulation, and we are trying to pass to Minkowski space-time starting from the Euclidean and Navier-Stokes, which yields the relativistic version of the Navier-Stokes equation. So for quantum field theory, now that the axioms are presented, then we need to find the actual examples that satisfy these axioms. Free field theories of any spin have been rigorously constructed without too much difficulty in the book of Forland or book of Barry Simon, or in many references. The Lagrangians may be written down explicitly as well. We show the cases of the free spin 0, 1/2, and 1 theories. First, free spin 0 theory is a free scalar theory, and free 1/2 is the Dirac-Spiner, and free 1 theory is a vector theory. Here, gamma is the any matrix that forms the Clifford algebra, which is defined by this relation. It is known that it is a mathematically known fact that such gamma matrices should be no smaller than 4×4. Also, F
No
mu nu
larger or no smaller?
no smaller.
Oh, means to solve that. Okay.
Yes. And F mu nu is defined as this, where A is the vector potential. So a brief comment is that the spin 1/2 for integer spins, the free Lagrangian is quadratic. However, for half integer spins, the Lagrangian is linear. Like, meaning that there is only one differential operator involved in it. And this is what Dirac found out, and Weinberg states that this is because of the probability density issue. In order for the half integer spin fields to have positive definite probability densities, it must have only linear Lagrangians. That's another mathematical fact. So, however, these are all free field theories. What about the interacting theories? The attempts to rigorously construct such interacting field theories or non-trivial theories are collectively called constructive quantum field theory. In order to simplify the problems, the founders, Professor James Gleam and Arthur Jeffrey, and possibly Professor Thomas Spencer and William Fairley and so on, they started working on lower dimensional space-time first, that is 2 or 3 dimensional space-time. The main result of the constructive KFT is the establishment of the 5-4 theory on those lower dimensions with full mathematical rigor. That is a scalar field theory with this interaction term, this interaction 5-4 term. However, in 4 dimensions, we have not yet yielded any non-trivial example, and the Navier-Stokes equation it's in lieu with this attempts to construct a non-trivial example in 4-dimensional space-time. So now we come to the gauge theories. So far, we have not considered the additional gauge structure that may be imposed on a theory. The Whiteman axioms do not encompass any gauge symmetries. Everything has been fully rigorous and is well established, though I have omitted some details. It is one of our current work to extend the Whiteman axioms to include a general gauge theory. From now on, the topics of ongoing research and unresolved problems will be dealt with.
You mean from now on in the lecture or from now on in your research project?
I'm still on a lecture, but some of the unresolved problems will be also presented.
Okay.
Still the main contents are very standard quantum field theory. So
I have a question about the
Yes.
history. So these BRST formalism and BV formalism.
yes,
And maybe after the millennium, these have been rigorously developed in some form, but for different axioms, like as a perturbative quantum field theory by Costello company, or maybe
yes,
people too. I don't know. I mean, the perturbative theory has been well established, can be defined in as well. Is the Whiteman axioms, that's a non-perturbative theory, right? That's a full theory, right?
right. Whiteman axiom is non-perturbative, right?
Yeah, okay. Yeah, so there's no non-perturbative 4-dimensional theory, even now, because the works I'm referring to are only about doing what is known in the physical level of rigor of giving a renormalizable perturbative theory, but doing it mathematically. Okay, so I just wanted to clarify the 4-dimensional case.
Okay.
Dennis, excuse me for saying so, but physicists will disagree with you. For physicists, there are well-defined lattice gauge theories which exist in 4 dimensions, and they are very well defined on the lattice. The gauge invariant, they exist. They are known to be asymptotically free, so they are adequate to nature. And another example which physicists would mention is the conformal field theories.
Excuse me, these are non-perturbative in your language?
Of course.
Yeah, okay.
And another non-perturbative example is conformal field theories, which not only are defined but solved. There are exact solutions in 4 dimensions which describe so-called conformal field theories, which also don't satisfy the Whiteman axioms because there is scale invariance on all scales.
Okay, thank you.
Okay, so let's continue. So the first is the simplest case of the gauge theory, the U1 gauge theory. Let capital P be a principal bundle over the base space S4, which is the one-point compactification of R4. We deal with the base space S4 instead of the ordinary R4 because from now on we need to consider a non-trivial principal bundle, and we need to impose some asymptotic conditions on the on the gauge potentials. These are related to the instantaneous effects. So on R4 there's no instantaneous effect, and the principal bundle is known to be trivial because R4 is contractible. So on each chart Uj of S4, let us suppose that there exists on a real valued one form Aj, which is also written as Aj mu dx mu, satisfying the consistency condition, which is written as this. Here, lambda ij. Oops, sorry for the flipping of the indices. Lambda ij is a smooth function on uj and intersection of uj and ui. Also, suppose that sigma j is some local section on uj that is well known that there exists a unique Riemann connection omega on P such that the pullback by each local section is equal to this A. You can recall that this curvature tensor, which is defined as the derivative of anti-symmetric derivative of A, is invariant under this gauge transformation 10 because the partial derivatives commute. So this curvature tensor is a bundle quantity or a global quantity. This is the geometry language of electromagnetism. The one form is the gauge potential or electromagnetic vector potential. This may be only defined locally. However, the curvature tensor, which is the electromagnetic field strength, is a physical quantity, and they are what we observe. They are defined globally. This is the Yuan gauge theory, and QED is the best known example of the Yuan gauge theory and it is the abbreviation for quantum electrodynamics, which couples this Yuan vector potential to the electron field. The Lagrangian is given as this, where the gauge transformation given as this has been imposed along with the gauge transformation for A.
So the electron field corresponds to what part of your notation?
This psi.
Psi, okay.
In the Lagrangian, partial mu plus IEA mu is called the covariant derivative and written as d mu. It is a straightforward computation to say that d mu psi transforms very simply as just like psi under these gauge transformations, and so that this whole Lagrangian is gauge invariant under the gauge transformations. At the level of physics,
So
this
wait,
theory
wait. So psi is a function, or is it a cross section of this bundle, or what?
psi is a function. Psi was originally a function, and we promote it to the cross section on the bundle by introducing this gauge transformation.
Okay, so invariantly it's the cross section of this bundle.
Yes.
Thank you.
At the level of physics, this theory may be neatly quantized, hence the name quantum, and is renormalizable using only gauge invariant terms. In the standard physics books, the renormalization process is carried on using non-gauge invariant terms. However, a thesis by Joel Feldman shows that the QED is renormalizable using only gauge invariant terms. It is like 180 pages thesis, but it shows that it finally shows that QED is renormalizable in a gauge invariant fashion. However, mathematically rigorous construction of QED has not been accomplished yet.
You mean in the sense of the Whiteman axioms?
Right,
In what sense?
in the sense of like,
Operator value distributions.
yes, operator value distributions, and we'll talk about this later. But in fact, this A, which was given as a, which I just treated as a ordinary function valued one form, actually should be operator valued one form. That's the question we raise. And in the sense of this question, problems and issues, QED has not been rigorously constructed yet. And now we come to general Yang.
I mean, even the elements, not much less checking the axioms, just finding the operator value one form. It's not been constructed.
No.
No what?
Not constructed in any
Oh.
basic sense.
I see. You can't start the rigorous proof because you don't have the elements. Is that what you're saying?
Yes, that's what I'm saying. So we are trying to construct the elements first. Also, there is a problem of if we promote, there's another problem that is very serious, which I did not really include in this slide, but it is that if we promote these operators, if we promote these quantities to the operators, then the Lagrangian is a composition of operators because the quantum field is an operator field distribution. For the free fields, the product of quantum field is well defined by the weak ordering. Okay.
So there's
Oh.
something called Wick ordering, which is what you use to define a product.
Yes,
I mean, we don't know what that is.
it is that the creation operators comes to the left of the line, and annihilation operators come to the right of the line. And by doing so, it is known from the book by Rudolf Haag that the completion of operators is well defined on the same dense subspace. However, for interactive theories, we cannot easily define such weak orderings because we do not even know that they are written as the expansion by creation and annihilation operators on some Hilbert space. So the product of field operators is a big issue, and this has not been resolved yet in the rigorous mathematical sense. And somebody asked that neatly quantized, it means that at the level of physics, QED can be quantized in either canonical quantization, which after getting rid of the constraints and leaving only independent variables, they can be promoted to operators which do not commute, or we can quantize them using the path integral in the same level of physics. And this is another very detailed topic of whole details itself, and so I just use the expression neatly quantized, and it means actually it means that the QED can be quantized in a way that every physicist agrees.
Okay, thank you.
Now we come to general Yang-Mills theory. We generalize the above framework to an arbitrary compact simple Lie group G, such as SU3. the generators of each Lie algebra G are denoted as TA, which satisfy the commutation relation given as this, where the summation convention is applied again. So that C, the index small c is contracted and it is summed. Here this capital C with indices A, B, C is called the structure constant, and it is totally antisymmetric in each indices. Now think of a principal G bundle over the base space S4. Now the vector potential AJ is a Lie algebra valued local one form given as this. Now there are many indices, so it can be somewhat confusing, but it is the best. But physicists still insist working with components. However, I try, because it is a mathematical seminar, I try to be as coordinate independent as possible. The consistency condition is given as this, where Tij is the transition function. Then the field strength tensor is given as this, or in the component as in the Weinberg volume 2, the field strength tensors have the components as this. So this is a generalization of the Yuan gauge theory. In the Yuan gauge theory, the structure constant was 0, so there was no term like this. However, in the general Yang-Mills theory, we have a quadratic term in the field strength tensor. So this extra quadratic term in the formula 17 gives rise to a self-interaction term in the Lagrangian, as we will see. The Lagrangian for the pure Yang-Mills theory must be Lorentz invariant and gauge invariant at the same time. According to Weinberg, if we exclude the parity inversion, the only choice is known to be this. Or in an expression more familiar to mathematicians, the expression is given as the trace. And with the suitable renormalization of the generators and the structure constants assumed.
Can you say what are the axioms of Weinberg when he says the only choice of Lagrangian is that? What is he assuming? What's the context?
He gets rid of a lot of terms, the condition that the theory should be renormalizable. So it should have, if it's not renormalizable, you can't do anything with it. So that's a constraint on the dimensions of things.
Yes, so he gets rid of higher dimensional derivative terms. Also, he gets off the mass term because a mass term is not gauge invariant. So he only leaves also if we allow parity inversion, then we may include the Levi-Civita symbol and a term containing it. However, as I said above, we only adopt the restricted Poincare group as our symmetry group. So the only choice is known to be this in the physical reasoning. This reasoning is at the level of physics, not at the level of mathematics. And if the Lagrangian,
some formal argument, if you had something that satisfied renormalization and you had everything, then it would have to not have higher terms. So there's a formal argument which can be made mathematically, making assumptions. Right? There's an argument.
Yes, that's called the power counting.
Yeah, right. But I mean, there is an argument, so there is a mathematical argument. It has to just be formulated. You know, we can distinguish between something which is rigorous at the level of physics that hasn't been completed mathematically because you haven't made the definitions, and one which one doesn't know how to complete. at all.
This is unique Lagrangian with the lowest number of derivatives.
Yeah, okay, okay. That's a math statement. That's a mathematical statement, even though you're a physicist. It's a math statement.
Unique gauge invariant Lagrangian with lowest number of derivatives.
Yeah, okay. Fine.
And that the formula 18 is gauge invariant is a straightforward but somewhat tedious computation. I can show you a sketch of the solution after this talk if you want.
Yeah, I
You
have.
may-
Can I make a comment here?
Yes.
I'm a topologist, and I started studying differential geometry. And when I made that computation 18 of showing that that curvature term is gauge, gauge invariant.
Yes.
It involves, it's like 16 terms and 14 of them cancel, and it's non-trivial. And I felt like I was the master of the situation then, because this is the only guy, and here's why it's invariant. It's a mini miracle, So
Dennis, it's totally trivial. If you look at the formula
no,
transforms covariantly and traces invariant.
Stop. It's not trivial. Not trivial. I'm advising Florian. I call him Florian, but his name is Raphael, who's listening. Do that computation. Take his transformation law. Can you go back to the previous stage? Here's the exercise you have to do. And then you have a union card in differential geometry. Can you go back to your previous slide where you have the transformation law for A? There's the transformation law for A. And then where's the definition of F? See, that's got two terms. It's got this T inverse, T and A, and then go back to the formula for F in terms of A.
Yeah, that's where they cancel.
Quadratic thing. So you have to substitute in the transformation law and see what happens. And all the terms.
They cancel, you have similarity
Don't say it's
transformation.
trivial. It's extremely important. If you say something's trivial, well, trivial is good, but it's sort of non-trivial because if you just calculate it out, you get many terms and they all cancel except the one you want. Okay, it's direct, but this is the fundamental computation of differential geometry, in my opinion. And if you do it, you are a differential geometry because everything depends on this computation. Even though
No, I agree with that.
Sasha says it's trivial. I like him saying that because it's extremely important. It's the only point that is non-trivial. Okay, go ahead. In my opinion, that's all my opinion. Okay.
Yes. From the view of physicists, because all indices has been contracted beautifully, it may seem trivial from the point of view of physicists that the Lagrangian is gauge invariant. However, from the view of mathematicians, we have to check everything carefully and in detail. So from the view of mathematicians, I agree that
it's an exercise. You have those two equations, the transformation law for A, the definition of F in terms of A. Then you want to get the transformation law for F and find out it's a tensor. In other words, in mathematics, when you prove something's a tensor, you've proved something. This is the curvature.
Dennis, let me say one word, if you excuse me. I said it's trivial because if you write the field, the F, as a commutator of two covariant derivatives, and you know that each covariant derivative is an operator which transforms by similarity transformation, then the commutator of two covariant things is also covariant.
Okay, I see. Okay, good. So then you reduce it to that state.
Yes, the math statement is that this formula for F is a commutator of two covariant derivatives. And that's in this form, it is indeed trivial to see that it is covariant.
Okay, so you're explaining why the cancellation takes place.
Yes.
Conceptually. Now you're being a mathematician.
And we may add external matter fields such as the proton, electrons, and various neutrinos and various other particles, which couple them to the Yang-Mills Lagrangian, which eventually lead to the standard model. The details are omitted here because they are very complicated. But what is important is that the Lagrangian for pure Yang-Mills theory itself already contains a quartic self-interaction term, as you can see from this and the above this. the two quadratic terms combine together to yield a quartic self-interaction term. And I heard from Professor Jeffy that this is where he believes the mass gap comes from. So let's let
Other
us
quartic
continue.
term?
Yes,
you-
the quartic
mass
self-interaction
gap-
term.
Say it again?
The quartic self-interaction term. That's where Professor Jeffy believes the mass gap comes from.
The mass gap.
Yes,
I mean, the quark confinement mass gap?
meaning there are many different definitions of mass gap, but I would define mass gap as the exponential decay of the correlation function, or the lowest energy of the particle spectrum.
Okay.
It has to be put in for low temperature only.
So quantization and renormalization at the level of standard physics. The quantization is carried out using the path integral, integrating out the gauge orbits and leaving what is physically meaningful. Renormalization is carried out introducing ghost fields to retain gauge invariance while using the gauge potential and matter fields which are not necessarily gauge invariant themselves. This is the BRST transformation, as Professor Sullivan mentioned. However, the path integral is usually an ill-defined object in mathematics because it uses a measure, infinite dimensional measure, that is very hard to define. There are some cases in which the measure is defined nicely, but in most cases, in most interacting cases, the measure is not really easily defined. Also, it is a belief of Professor Lim and I that the ghost rise on unnecessary complications. We believe renormalization, just like QED, may be carried out using only the gauge invariant terms. That's what we are working on. So problems that we point out. The path integrals is usually an ill-defined object in mathematics. Also, we think that ghosts arise unnecessary complications. And lastly, the connection one forms. I treated them just as ordinary functions. At the classical level, this is okay. But as mentioned above, if we pass to the quantum theories, we cannot define a quantity pointwise on the space-time. So if we want to quantize a vector potential, then their components should not be ordinary functions whose values are operators. They must be operator value distributions. And so the vector potential must have operator value distribution components. So our current research is that first, it is my main work to extend the result established by Weitman to the gauge theories and principal bundles. This includes the notion of Weitman functions, the reconstruction theorem, and the operator value distributions, as I just mentioned. Also, it is the main work of another collaborator, Gerard, and Professor Glim, that we are investigating how to write down the renormalization formula entirely in terms of gauge invariant quantities. This is carried out using the Kubo cumulants and Bell's number. We are noting that the terms in the Lagrangian themselves can form the Kubo expansion. Also, we show that the renormalized perturbation theory and the ultraviolet limit to continuum theory are compatible in the sense that it does not matter which limit we take first. More specifically, we start the first renormalized one particular irreducible state, which is logarithmically divergent, and apply the method of its construction to the vacuum expansion. Then the expansion becomes finite for RPT of order equal or greater to 2. So we do not need a subleft norm of negative index. That's what everyone has been complaining about, because subleft norm of negative index ruins the gauge invariance. So our eventual goals are Navier-Stokes equation and the mass gap. We all note from an unpublished Indonesian paper the U1 gauge theory coupled to the scalar field instead of the Dirac spinor. Here's the relativistic version of the Navier-Stokes equation as the equations of motion. we are rigorously constructing general gauge field theories in 4-dimensional space-time, which satisfy the extended Whiteman axioms that I have been working on. Thus, we aim to incorporate fluid dynamics and the existence theorem of Navier-Stokes equation into the framework of gauge theories. Also, there is an important unproven property of Young-Mills theories called the mass gap, which establishes the exponential decay of the two-point correlation function according to distance and leads to the cluster decomposition property. This is a very brief definition of a mass gap, but there are many different definitions of the mass gap, as Professor Sullivan pointed out. However, they are all known to be equivalent. We are making attempts to utilize the concepts and ideas of fluid dynamics, such as the energy dissipation and so on, to show that the mass gap indeed exists for Young-Mills theories. So this is the end of my talk. Thank you for listening.
Minshall, I have a question. You mentioned one of your collaborators is James Glim. Who are your
Yes.
other collaborators?
Excuse me?
One of your collaborators is James Glim. Who are the other
Yes.
collaborators?
He is Gerard. He is another student of James Glim, Professor James Glim.
Okay, so you're doing work with James. Okay.
I have a question.
Yes.
Can you show me how Navier-Stokes equation is related to U1 field theory? I haven't seen the formulas.
Okay, I'll share. It is from the Indonesian paper, and let me share the screen of the original paper, original
Yes.
Indonesian paper. Okay, and
I'm just wondering because I don't know where there's gauge invariance in Navier-Stokes equation. I don't know where is U1 symmetry. So I'm very. Can you send me? Yes, please send me that.
okay, let me share. I will send you the text after this talk. But let me
Okay, thank you.
let me first show you this. So so this is the correspondence.
I
So Navier-
understand. You think that gauge potential is a velocity field, but I don't understand how gauge invariance enters the game because there is no gauge invariance in Navier-Stokes equation.
In fact, for Navier-Stokes equation, the gauge in the
Can you read off it'd be interesting for the audience to read off the left column and the right column in terms of their names, maybe. Like B is blah, blah, corresponds to blah, blah. What's that?
B, the magnetic
Magnetic
field
field corresponds to vorticity, electric field.
No. I asked been to the lecturer. Let's
Okay.
do it
and electric field corresponds to the Lamb's vector and the
What?
vector potential Lamb's vector.
Well, that's no good.
And the
Same with
vector and the
you've
vector
all heard of electric field, magnetic field.
and the vector potential corresponds to the velocity field is velocity field. And in fact, for Navier-Stokes, the gauge invariant. I admit that the Navier-Stokes equation does not have a gauge invariance. For Navier-Stokes equation, each gauge fixing has a physical meaning. For example, if we fix a Coulomb gauge in which the spatial part of the vector potential has zero divergence, then it corresponds to incompressible fluid. So now there is some difference between Navier-Stokes equation and U1 gauge theory. However, we note that at least the equation of motion can be derived from this Lagrangian, which is gauge invariant.
Well, so if there is no gauge invariance, then it is not a gauge theory. So
No,
Navier-Stokes equation has
wait.
nothing to do with the gauge theory.
Wait.
It's not gauge theory. Navier-Stokes equation is not a gauge theory. Now I understand it.
Well, no, but those phrases don't mean anything to mathematicians, okay?
There is no continuous invariance in Navier-Stokes equation, period.
No, but that's not the point.
Well, that is the
Not
point.
the only point, Sasha. Isn't it true that you have a constraint? If you want to try the action principle, you have a constraint. Divergence is 0. This is a constraint.
That's a basic constraint. That's a basic constraint for incompressible fluid, and
No,
that is
of course, it's a basic constraint, but it's if you want to apply the action principle and you have a constraint, don't you have to gauge the constraint to make a free theory so you can apply the variational principle to get the equation of motion?
yes.
And when you gauge that constraint, in fact, I started noticing that the physicists around Stony Brook, when mathematician says gauge theory, he now, what they mean is a certain theory of bundles, connections, curvature. That's what they mean. And gauge there is used as an adjective. And I noticed talking to Martin Rochek that they use the word gauge as a verb. Okay?
Yes, right.
So I mean, I have such primitive understanding. I'm using the most basic things, like a 2-year-old. Daddy uses this as a verb. It must mean something else. I only thought it was an adjective. Okay. Now, so then I looked up online, let's gauge, what is he gauging? And I guessed maybe he's gauging the constraint. And I looked up gauge the constraint. Okay. A verb, gauge the constraint. A noun, do this to the noun, gauge the constraint. And I got a whole slew of references to physics. And then I kind of understood something. And that something was when you can, here's something this is something close to a topologist's heart, but if we work on periodic 3 space, which is basically working on the 3 manifold, which is the torus, the first Betti number is 3. You have 3 homology classes. Your fluid can have net rotation in 3 different parameters. Now let's go ahead and suppose all those parameters are 0. Let's work with a fluid initial condition, which is divergence 0, and it's also homologous to 0. It has no homology. There's no net rotation everywhere. And this is an implicit assumption often made and not specified. Now, when you use the Biot-Savart law with the pressure and so on, you're preserving that condition of homology. And that's what makes the whole thing well-defined. So now that's what makes the whole discussion coherent from a math point of view. Okay, otherwise there would be these extra parameters you'd have to deal with, which is not difficult, but it's a certain point. Now, if you work with initial conditions that are divergence-free da-da-das, which are homologous to 0, then you can write them as the boundary of something. And then you can choose something whose boundary is that. And this is like choosing a potential. And it's ambiguous. And the set of ambiguity is the set of things you're writing it of the boundary of, which have boundary 0. So there's a space of boundary 0 objects whose boundary is giving you this object, and that is the gauge group. So if you if you do it that way, you get a free theory, and then the translation by the linear space of elements whose boundary is 0 is the gauge group. And that's what gauge the constraint means in this context. That's what it could mean.
That's the global gauge group, but the idea of gauge theory is you'd want to make it into a local theory. So you can do these transformations locally.
Yeah, but then you have a trivial bundle and you can do it.
Well, in fact, you should have a trivial. You should have a trivial bundle. You don't want to bake in the topology from the boundary conditions. So you should have a trivial bundle, and then something happens or doesn't happen on the basis. The theory should have a trivial bundle. It's a better theory.
No, but you're adding an additional remark. I'm getting the discussion started with Sasha that there's a constraint here, and the physicists have this verb, gauge the constraint, and then you can start gauging the constraint, and it has a perfectly clear homological description, just like, you know, all of this stuff in bundles and curvature has a homological description too. It's sort of nonlinear homology, but this is what all this BRST and BV stuff is about. It's very similar.
But my question or my statement was very simple. There is no local gauge invariance in Navier-Stokes, and there is local gauge invariance in electromagnetic field.
I know that's your statement, and I'm saying you can give a different presentation of it, which has local gauge invariance.
In Navier-Stokes?
Yes.
I'd like to see it. I don't see it.
Euler.
Oh, I noticed that the vorticity is a quantity that is gauge invariant. The Navier-Stokes and the Navier-Stokes equation in its relativistic form, after some manipulations, it contains the vorticity. So
no, it also contains velocity. In whatever form, if you write Navier-Stokes equation for vorticity, it still has velocity, which is not a gauge invariant. There is no gauge invariant Navier-Stokes equation. Am I crazy or something?
No, wait. You're just making a statement, but you know, you're not on the same, you don't have proper definitions to communicate. There could be a presentation.
No, I was asking, what is gauge invariant Navier-Stokes equation? I'm not seeing
it. Could be a
it.
presentation. You cannot prove, there is no presentation of a gauge theoretic, of a theory, of classical theory that has a gauge field in it whose equation of motion isn't equivalent to the Navier-Stokes equation. That's what you say there is no, you're implying that you can't even do it that way. And you can't prove that, I'm sure.
Well, you can't prove it because it isn't true. These people have
Exactly.
proved that it is true.
Right, but
That's
I mean,
why you can't
I'm
prove
just
it.
trying to clarify the discussion, okay? But anyway, you can see, there is no, you know, if we make this a math discussion, you can't argue very long. Look, I've seen physicists argue all afternoon about something, which was, I realized was obvious. They didn't understand what a quotient vector space is. They didn't make a distinction between a quotient vector space and an orthogonal complement. And if they had made that distinction, they would have stopped arguing. If we make a precise math statement, and then it's either true, if it's precise and you both agree on it, and one person has a claim proof that it's one way, and the other person has a counterexample to that statement, then they stop arguing. If you make your statement precise, and then he gives a counterexample, you stop arguing. You don't argue anymore. So make it precise.
Okay, let me try to make it precise. I'm asking, I'm not making a statement. I'm asking.
Oh, you made a statement. You made a statement. You said,
okay, let me make a statement.
There's no gauge.
Okay, let me make a statement. The equation of motion, the Navier-Stokes equation for vorticity is not gauge invariant.
What does it mean, that statement?
If you make transformation of vector potential by adding gradient term to vector potential, Navier-Stokes equation for vorticity does change.
Look, Sasha, you can formulate the equations so there's no gauge visible, and you can formulate the equations over again so there is a gauge. So
I want to see that equation. I'm asking, please show me this equation.
10 pages long, and it does derive the equations of motion as you like them from a formulation that does have a gauge in it. And it
Gauge invariance or gauge?
It all starts with the elliptic theory. I'm sorry there was so much Minkowski stuff in this, but it's all elliptic. And it uses the Coulomb gauge, and in the Coulomb gauge.
Coulomb gauge is not gauge invariance. Coulomb gauge.
Coulomb gauge is not gauge invariant because it fixes a gauge. Coulomb gauge fixes a gauge. And the derivation of the Navier-Stokes using a gauge theory fixes the gauge in the Coulomb gauge. So the gauge is there and then it gets fixed. And there's about 10 pages that prove this. And I don't see where you.
Okay, I'm sorry, I don't want any more interruption because apparently it cannot be described here. I will read it and report. Thank you. Now that I will have that paper, I will read it and then I will know what we're talking about.
Okay, as Professor Glim said, this is the original equation of motion, which more looks like gauge invariant form. However, the paper does some manipulations and it fixes the gauge so that it yields an Navier-Stokes equation which may not be gauge invariant. That's what.
Once you fix the gauge, it's no longer gauge invariant.
Excuse me?
Once you fix the gauge, it's no longer gauge invariant. It's derived from a gauge invariant theory, but it.
Well, gauge theory, even if you fix the gauge, is
Hey,
invariant
Sasha,
under
don't
the
interrupt
choice
in
of
the
gauge.
middle of a sentence. Sasha, stop it.
I thought you
Finish
said it.
sentences and then interrupt.
Once you
know what
fix
you're
the
saying?
gauge, the theory is no longer gauge invariant, obviously. It is derived from a gauge invariant theory, and you fix the gauge, and once you fix it, the gauge fixed theory is not gauge invariant, but the ultimate derivation comes from a theory that is gauge invariant.
Let me answer that. If you fix the gauge in the gauge invariant theory, then the result would not depend on the choice of the gauge you fix. And that is a very important difference. If you could fix any gauge in quantum gauge theory, but the result is independent of the gauge
I'm going to
fix.
stop this discussion because the word gauge.
Okay, look, I understand.
The word gauge has not been defined. Gauge
No,
theory
I
has
will.
not been defined. What you're talking about has not been defined. Let's stop this. We do not discuss
Okay,
this way in mathematics.
Thank you. I'll rather read that paper and report. That would be much more productive. Thank you.
Okay.
It's all Hermann Weyl's thought for inventing that word. Gauge theory.
And in the chat, somebody asked about my current approach to operator value distributions. It is that it is a distribution, which means that it is not a function and it must be smeared. Professor Lee does not like the word smear. It must be convoluted with test function in order to get its value, yield its value, but its values are operators, densely defined operators on some Fock space. And
that is a correct statement, and that touches on ongoing topics of research. So I'm not going to comment further.
Is the mathematical difficulty defining the measure? Or you said this was sort of like a core mathematical.
Well, there's a lot
difficulty.
of different ways of going about this, and there's many, each one of them has its own difficulties, but I'm not going to discuss things that are still under investigation.
Minshall, I saw that the paper you were reading has University of Oxford
I'd like to
on
make
it.
a criticism of that last remark. You know, when we're discussing definitions and well-known things, they can be discussed openly. If there's something you don't want to discuss, don't just say, you know, I mean, there's a lot of things people here don't understand. They can all be explained. The idea of an operator value distribution can be defined. This goes back to the 60s. Don't say that I'm not going to talk about it. It's current research. It's not nice.
Well, the axioms that Ren is developing will make those notions precise at the level of axioms.
No, but an operator value distribution, that all those words can be defined now. I think that's what was being asked. I don't want to curtail the discussion on that. That's public domain material. Come on, this is not nice.
yes, they they are defined rigorously on the R4 or any Euclidean or Minkowski spacetime, but they are not yet rigorously defined on the principal bundle. And what I'm doing is to define them rigorously on the principal bundle, and still on R4 that it is very well known that operator value distributions are well defined, and it is that. Okay, let me show the. Oops. Let me show the exact definition for exact definition for the original case of Arthur Whiteman. Let me see. Here. This is the definition of operator value distribution on R4. Phi is an operator value distribution if it is a linear map. It is not just a map. It is a linear map from the short space, the set of linear operators on some Hilbert space. F is a Hilbert space such that for all F we have some dense domain. We have some dense domain with nice
That
properties.
should be N and M, right, or not? Or, oh, that's the adjoint? What's that?
Yes, yeah, dagger is the adjoint.
Okay, okay.
And for all elements of the domain, this map is a temporal distribution on R4. This is the definition of the operator value distribution on R4, and I'm working in order to extend this definition to the principal bundle.
Okay, but that you don't even have to say if you don't want to talk about it. So, okay, and then I think Raphael was also wondering, well, what's the problem? Because it's a measure or something. So the point is, these things don't form an algebra. Yes.
No, they don't form. We do not know that they form some structure, but for now on, they do not form an algebra.
And these are important because you want to have a well-defined notion of sampling a solution. So these are representing solutions to the equations, and you want to sort of sample from that space.
He's asking, why do you want to have an algebra structure? From the physics point of view, why do you want to have an algebra structure? Man.
Because then it is much easier to find the symmetry, find the symmetry, hidden symmetry of the solution and of the theory. However, for now, the operator value distributions do not exhibit any such structures from what I know.
Okay. Okay, I'm just
And-
trying to tie this back to sort of sections of like the tangent bundle. So you could think of like, you know, your solutions to ODEs, you take a section, and then this is somewhat describing sort of a, like when you say tempered distributions, it's almost like you're sampling. You want to be able to sample sections of, you know, the tangent bundle to get solutions to your ODEs.
Oh, sorry. Before you go off on another idea, wait a minute. You didn't answer, Min, you didn't really answer, because when you go back to the Whiteman axioms, you have something about the light cone, space-like, and the operator's commute, right?
Yes.
Okay, go back to there, please, that axiom. Can you find that axiom? Five, axiom 5.
Yes.
Okay, so to even make sense of that, you have to compose two operators. It means you do one, then the other, and then reverse the order, and they get the same thing. That's what commute means.
Yes. So that's where I.
No, but I mean, you have to tell them that. That's why you want to know whether it's an algebra. You can't make sense of this otherwise. At least you want to make sense of the commutator.
Well, I think in the sense you're talking about, it is an algebra. It's a dense products of densely defined operators form with a common domain that's invariant under the operators form an algebra. So the reconstruction theorem gives you an algebra.
No, the distribution valued.
The axioms themselves do not give you an algebra, but in any direct sense are very meaningful. But when you do the reconstruction theorem, which constructs the Hilbert space out of the Whiteman functions, then you get an algebra of operators. So it's one step beyond the axioms. The proper definition of the algebra is one step beyond the axioms, but usually considered in the same context.
Okay, but the point I'm making, there's an elementary math point here. It's sort of like you can multiply two functions, but f and g, but if you looked at f of x dx and f g of x dx, as you look at these instead of functions as being measures, then you can still multiply the f and the g. But if you just have two measures, you can't multiply them. So you can multiply smooth measures, but you can't multiply. You can choose a dx, and then you can write the measure, a smooth measure, as a function. Then you can multiply.
You have to regularize each of the x's. When you multiply, you have multiple x's, and they each have to be individually regularized by a test function.
Yeah, but then the multiplication will be not commutative. Will be, let's say you can make it commutative, but then it won't be associative.
Well, I don't know.
Won't even
I don't know. I just haven't thought all these things through. I'm just telling you what I know.
No, but I'm saying look, this is a math graduate student. I'm telling him this is a fundamental point that you understand, that I keep calling you Florian, Raphael. You just think of the difference between smooth measures. If you have smooth measures, you have density functions, and then you can multiply them. But if you were just talking about more general measures, you can't multiply them.
Well, you can, because you have products of operators. They're smoothed independently. You have two of them with an x and a y. The x and the y are smoothed independently of each other.
Yeah, you can make choices to smooth them out, but then you won't get an algebra structure on the original set of objects.
Well,
And even do it for measures. I'm going to the first bit of irregularity that ruins the algebra structure.
Well, I'm just not going to comment because I haven't thought.
Oh, no, you are commenting. If you don't comment, then just don't say anything. I'm teaching him something.
Yeah, all
That's
right.
the point. I mean, I remember I was a graduate student at Princeton in the 60s when I heard about this, and everyone was going around. I didn't know what the hell they were talking about. The physics was right next to the math department in Old Fine Hall, and they were going around, you can't multiply distributions. That's the problem with constructing these things. And I said, okay, fine. And then I found out later when I started studying Navier-Stokes, gee, you can't multiply these negative Sobolev spaces. And that's the problem there too. And then there's another problem we have in topology, which is called give a combinatorial formula for the characteristic classes. And the fact that you can't multiply distributions is the problem there too. So here's three problems that all have the same issue. There is no algebra structure. And I like that point. And that's what I'm talking about. And it's very clear measures. It's fundamental. I mean, you may get around it somehow with other axioms, but this is a fundamental point. And it shouldn't just be, you ask the question, you get some silly answer, and then change the topic, Raphael. It's a serious point.
Okay, let me clarify. this is the exact statement. I am not multiplying the distributions. If f and g are in, this is the exact statement, because maybe confusion arose because I used the informal language of distributions. Let me use a more correct language. If f and g are in the short space and the supports of f and g are spacelike separated, meaning that x minus y is spacelike whenever this is non-zero, and as operators on D, you notice that phi mf is an operator. It is already evaluated. It is a distribution that has been already evaluated to be an operator. So we evaluate the operators, not the distributions. So we don't have to really think about an algebra. We just think about the operators and their compositions.
Okay, let me see. Vm is what? An operator value distribution?
Yes.
Okay, so that gives you an operator.
Yeah, for each f, phi mf is just an operator.
With a given domain. With the
Yes,
same
and the domain is
common domain. Okay. All right. So that makes sense. Okay.
yes. Because the slide was because slide is limited. I had to be somewhat informal about the definition. So sorry about this confusion, but this is the exact statement.
That helps a lot. Thank you. I really appreciate it. Thank you, man.
Okay.
Oh, okay. So I see the domains, they have a common domain.
Yes. As the first axiom points out, all have the common domain.
So let me see, but still, is it still true that you can form the composition? That's about the commutator. You're saying the commutator is zero. But suppose you just form the composition.
Yes. That's the assumption. That's the assumption that we are able to form the commutator.
Just say, suppose you have two distribution valued up, and everybody has a common domain of definition.
Yes.
Then on these Schwartz functions, right? So then wait, the composition, the operator doesn't take the domain into the domain, does it? How do you
Yes.
compose? See, you can't compose, right? The operator is defined. No, but when you compose, you have to take the image.
The operator takes the domain into a subset of the domain.
Why is that? That wasn't written anywhere.
Well, I'm talking about the reconstruction
Oh.
theory.
Oh, sorry about that.
No, but I'm talking about I'm shocked that I say I'm illustrating this in a case. Okay, so see, if you just have two operators that have the same share a dense domain, can you form their composition?
Oh, sorry about this. They are and their image should be also included in this domain as well. That's part of the axiom as well. Sorry about not including all these details.
Well, they take the domain into a subset of itself.
Okay, well, that's another axiom. But if you just have an operator value distribution with, and suppose you even have, they all have dense domains of definition, without this axiom, you can't form the composition.
No, that is not possible. So I admit that I omitted those details.
Right.
Well, it's all here. Yeah, it's as you highlighted.
The difficulty of Navier-Stokes equation is that you're working in spaces with limited regularity, and there's differentiation going on inside the formula. So you go out of the space when you apply the operators. You differentiate, like a C1 function, differentiate, you just get a continuous function. No longer has a derivative. That's what you see all the time. So I guess they're sort of hoping that, I think they're hoping that, I remember some theorem of Nelson that a very general setting, there's always the real analytic functions in some very general case form a dense set of where things are defined for a large class of things. And of course, there, if you differentiate, it's still real analytic, but yeah, it's still real analytic on the same domain. Well, I just remember as a graduate student being told that since you can't multiply distributions, that's why they can't make these constructions of constructive field theories. That was told to me in 1964 in Fine Hall in Princeton, with Wigner standing there and Barkman standing there and other Gunning and analysts, Bachner. So
You can't multiply, what's the end of the sentence? Then you can't what?
you can't multiply distributions. That's, I mean, this sort of, that's a problem. So
And
Yeah.
I am aware that certain techniques have been developed to multiply the distributions.
yeah,
That
yeah, you
give me
can smooth them and then multiply them, and that'll be commutative, but it won't be associative.
I don't think there's any problem with the Whiteman axioms. They've been verified, for example, in 2 and 3 dimensions, probably in
No,
3.
no, it's not problem with the axioms. The statement was the reason they're hard to fulfill is this issue about distributions. That was the statement, whether it's true or false. That was the statement. So, and I think it's also the fundamental problem in nonlinear PDE. You can't multiply rough objects. And that seems to be the problem.
Yeah, but I don't think it had anything to do with this axiom. It's unrelated. It's related to something, but not related to this axiom, which is perfectly correct. It's
Well, the
related to something else, but it's not related to this axiom.
The statement in the 60s was it's difficult to satisfy these axioms because you can't multiply distributions. Now, that because we could put aside, I just heard it, and then we heard in this lecture, it's still not done rigorously in dimension 4. Okay, so there are some difficulties.
Well, correct. Nothing much is done rigorously in dimension 4 from this point of view, but you can do it in dimensions 2 and 3.
I know that's the famous work of somebody in this room right now.
Yeah.
And I haven't actually, Professor Glim and I have some ideas on how to work this out on dimension 4 by using the generating functional method.
Okay, well that'll be exciting to hear about.
Not today.
Yeah, no, I know. Vincent, what do you want to do now?
If there are no other
Well, wait a minute. Wait, no,
comments.
I don't like that. Wait a minute. There are no other questions. No, I mean, go back to the beginning. I mean, where Min-Chu Lee was giving this nice overview. I mean, maybe there's some more discussions at the beginning we could do next week or something. I don't know. Beginning was a nice survey of. Can you show me your first page again, Min-Chu Lee?
Min, you had mentioned relativistic Navier-Stokes. Is that the outcome of when you start thinking about Navier-Stokes dictating the motion of these electrons or these sort of quantum like particles? Is that where you need to have the sort of relativistic Navier-Stokes come in and the terms get replaced with operators? And there's a whole complication there that arises because you no longer think of things as like a vector. You're now thinking of things as like operators that are evolving.
Partially,
guess-
yes.
Okay. Yeah, that'd be really, and that paper that you pointed us to, is that described in there as well? This idea of particles as operators and Navier-Stokes governing the motion of those. I don't know what you call them, particle operator things.
Field operator.
Okay. And experimentally, does the relativistic Navier-Stokes get verified through astronomical observations when like stars collide, or how does the relativistic Navier-Stokes?
The relativistic is not, that was a misuse of the word. The Navier-Stokes is not relativistic, but it comes from the Euclidean formulation of a field, of a quantum, of a gauge theory. So I don't think the Minkowski operators are, I think are a little bit of a side issue. It has nothing to do with relativity and Navier-Stokes directly.
Oh, okay. That helps a lot because I just saw relativistic Navier-Stokes.
Yeah, well, I
on this first
objected
page.
to that, but I didn't get it out of this lecture.
Oh, okay, thanks. Okay.
But there is a relativistic Navier-Stokes equation, right?
That's a separate issue.
No, there is one though, right?
I know it, but I think that's an unrelated issue. I'm not sure. Maybe it's related.
Well, no, but I mean, we can
Maybe-
talk about it,
maybe-
whether or not it's related in some sense that you perceive.
Yeah, maybe
There-
you're right. Maybe it is.
No,
Maybe
no,
it is.
I mean, no, I'm just there. I mean, suppose you had, I mean, I think for Raphael's question is, is there some astronomical discussion which involves, you know, some kind of fluid in sort of equally distributed, some, you know, moving in Einstein's framework or something, and giving a relativistic version of what you might call the incompressible fluid equation. Is there such a thing?
Well, everything must be validated to some extent. Experimental validation is never perfect, but there must be something there. I don't know the answer to your question.
Actually, I had a question about something you mentioned towards the end. Actually, at the end of your talk, Min-Chu.
Okay.
In the very last slide. Yeah. So you had mentioned that so one is you can realize Navier-Stokes in this, QFT formulation or framework. And then secondly, that you hope to address some questions in QFT by using ideas from fluid dynamics. I was
Yes.
wondering if you or Jim would be willing to comment on what fluid dynamics questions you hope that this, new perspective could attack or hope to answer.
I'm not going to comment on future work.
Okay.
I have a very simple question. What is the University of Oxford doing on a paper being presented from a student at NYU? I don't understand that.
Oh, actually, I got my master's degree from NYU, and I'm going to go to Oxford this September. So I already graduated from NYU, and I do not belong to anywhere right now. So I just put University of Oxford because I am bound to go to Oxford this September.
As a doctoral student of mathematics?
Yes.
Mhm.
They have fluid dynamics there.
Yes.
Who is this in math or physics or applied math? Where is it? What department is it in?
Mathematical sciences, Hui-Chang Chen is well known in fluid dynamics.
Oh, okay. It's called
I believe
mathematical.
Saragin.
It's called mathematical sciences, the department.
Yes.
Is that like? Well, what does that mean in terms of American boxes? Applied mathematics and pure mathematics mixed together?
It's
Or?
a mixture of mathematics and computer science.
Oh, okay. Sounds good.
I have a comment on the sociology of science. If you look closely at the references, you'll discover that the master's thesis has one author with two advisors, and the follow-on paper has the two advisors and does not list the master's student who wrote the thesis.
No, you mentioned that before. I think he did mention that in the paper.
Yeah,
It's in the
anyway,
paper.
that's just curious.
No, I think in the paper they did mention somebody like that.
I didn't see it in the archive paper. I didn't see his name mentioned at all.
Okay. Do you know what his name was?
Perush something or other. I don't know. No, it's an Indonesian name. It doesn't stick in my head.
Okay. Yeah, I remembered that point, and then I think when I was reading the paper, I thought I saw something that could have been it.
Well, okay, then maybe have to modify my.
No, I don't know. I'm not sure. It
certainly doesn't show up in the references.
Yeah. Did you manage to get a copy of the unpublished work?
There's nothing published. There's an archive paper and there's a document from the university document from the master's thesis.
Did you get the master's thesis document?
Yes, I got the master's thesis copy off the web.
Okay, I see.
Professor Sullivan.
Yes.
So I think that you must be acquainted with Professor late Arthur Whiteman, right?
Yeah. Well, I was just a graduate student, and he was in the common room for tea many times. But and I talked to him, but I don't. Yeah, yeah. I mean, I talked to him, but just chat, polite conversation. I was not prepared to understand the Whiteman axioms. But all the time I was at Princeton, he was around. Yeah. Also, Wigner and Bargman were around also.
And Professor Jeffy as well. I mean.
I guess I know. Yeah, I've known Jaffe from various places. Yeah. Oh, because he's like more my generation. Because I was also in Boston for a while, and he was in Boston, and he was in Princeton, and he was in France often when I was in France at IHES. I remember him coming into the lunch one day talking about monopoles. And then we knew about the constructive quantum field theory work. We heard of it. I didn't know what it was about, but I mean, we heard of it. And the fact that it was, you could do nonlinear theories up, including dimension 3, but not quite dimension 4.
How about dimension 1?
That's quantum mechanics, not quantum field theory.
This Lagrangian that you derive the equation of motion from, or I guess the Indonesian paper does, that gives you ultimately this Navier-Stokes, pops out Navier-Stokes as the equation of motion. Is there a well-defined way of probing the Lagrangian to get useful information about the equation of motion? As in, can you learn something non-trivial, or maybe even trivial? I don't even like the word trivial. Can you learn anything about the equation of motion by probing at this Lagrangian level?
Excuse me, do you mean the solutions of the equation?
Well, I learned something, and that is that the matter field has the role of a forcing function. So the Lagrange equation of motion could have a forcing function if you wanted, and that's what the matter field does.
Okay, I guess to answer Sullivan's question, yeah, my understanding of the presentation, or at least the starting point of this research direction, is there is a gauge invariant Lagrangian, out of which pops out the Navier-Stokes equation as the equation of motion of this sort of parent Lagrangian. And so yeah, that's what I was talking about. That's really interesting, Professor Glim. Okay, that's okay. So beyond that, is it useful to sort of study the Lagrangian itself and then sort of translate those results back down to the Navier-Stokes equation? Like, could you reformulate finding solutions to the Navier-Stokes equation as having something to do with the Lagrangian?
Well, we believe that renormalized perturbation theory, which is one of Feynman's main contributions, is fundamental.
Fundamental in making that connection between understanding.
Well, we're still getting new results, but I just think it's going to be fundamental to anything we do.
And this Lagrangian, is it unique in any sense? Like, is there a nice sort of theorem to say, hey, there's another sort of gauge invariant Lagrangian out of which its equation of motion would also give rise to the Navier-Stokes equation?
Well, that question came up earlier. Weinberg considers possible alternatives and throws them out for one reason or another. It's not a mathematical discussion, but it's a physics discussion. At the level,
yeah, I remember.
Level of physics, I think it's pretty much unique.
Yeah, I'll be excited to see when you are prepared to talk more about it, I guess. It's pretty tight-lipped right now. Okay.
you go to page 1 again, page 2 of your. All right, okay, and then go for, wait, can you go back 1 page? Okay, so this. The quantum field is spread over space-time, right?
Yes.
But if it's only time and no space, then it's not called a quantum field. It's called a quantum mechanics or something.
You can often take the Coulomb gauge, and then you get you have time as a distinguished variable. You have a Hamiltonian and so on.
Now, could you go to page 3? Skip the index parts, the indices. Yeah, okay, here. Okay, then go to the next one, please. Okay, go to the next one. Okay, go to the next one. Oh, then here's the axioms. Go to the next one. Okay, so then there's Osterwalder Schrader. So is your theory going to satisfy these? Oh, I see. If it satisfies, are you hoping, is this work in progress too, that these 5 properties will be satisfied by your theory?
Well, that would be an ultimate objective, yeah.
Okay, fine. Okay.
But they have to be reformulated first. They're not correctly formulated for gauge theories.
Yeah. Okay. Oh, I see. These have to. I see. That was one of your projects, right?
You know, reformulating these for gauge theories is itself unknown.
Yeah. Okay. Unknown in the sense that when they're reformulated, they would apply. You could go to the Lorentzian framework from the Euclidean framework.
Well, that's the reconstruct. That's the that's the equivalence theorem, the Euclidean to Minkowski equivalence. And so I don't know how ambitious the theory will be, but a complete theory would have that.
Well, it's interesting. I mean, in math, all the mathematicians, there's a whole field of math between theoretical physics and rigorous mathematics. It's a big activity. And most mathematicians that are not in that, well, they're happy with in that discussion, they often do the Euclidean version of the theory. And I've never seen them discuss this reconstruction aspect. I mean, that would be interesting. I mean,
well, in fact, there are some problems there, and so I don't know exactly how that's going to pan out. But in any case,
well, no, but I don't want to impose on I'm not trying to impose on your project. I'm just wondering, this Osterwalder Schrader thing, this is a theorem, I would guess, right? This is a rigorous theorem.
well, they have sometimes they need some level of analyticity to do the analytic continuation. And they may or may not assume things that are inappropriate. But I think it was okay for 3 dimensions. I think it was proved in 3 dimensions, so it's probably okay. There's a special version for 2 dimensions, and it's unique to 2 dimensions. So you can't, if you assume too much analyticity, it's simply not true.
So I would like to hear what these first 4 sound like you just state what they are. The 5th one is some intuitive thing. Like to Could we hear more about that next week? What it means intuitively, just as an axiom?
You mean the cluster decomposition property?
Yeah, yeah, just what does it mean? I mean, could you talk about that next week? Just as a definition in this Osterwalder-Schrader theorem.
Well, that's the statement that what happens at a remote distance has negligible impact on where you are.
Okay.
So this is, there's this theory about the butterfly in Beijing that influences the weather in New York.
Right.
And this is a statement that is negligibly important according to the distance between here and Beijing.
Well,
I heard that the phi-4 theory,
in mathematics, there are these things called cluster algebras, and that's the whole subject. So since you have the same word here, I'm just wondering if.
I don't know, what's a cluster algebra?
I don't know. I don't know. I mean, I have some vague picture, but it's
There's a
something
theory of
something
Hopf algebra
correlated.
that you're talking about,
What?
Hopf algebras?
What?
No, all right, I don't know the cluster algebra.
I mean,
I don't know what you're referring to.
I do not think they are related.
you don't?
I do not think.
Well, I think they are, because the people who work on them are the same people in this area between quantum field theory and mathematics. So, and this word has been around for a long time. How old is this word? Is this the way it was described in the 60s? Or this?
Yes.
Yeah,
Okay. Well, I mean, the people who do this, largely they're from the Russian school. They're in the physics milieu, so it would be surprising if it weren't related. Maybe in a trivial way, but I mean.
Go back to fluid dynamics for a second.
Wait a second, just a second.
Oh, sorry.
Wait a second. So see, if you're a mathematician and you're trying to learn this stuff and you hang out like at the Simon Center with people who are giving in this group between theoretical, Witten's work and all these particular theories, and they're always talking about the Euclidean version. And we all know you're supposed to have causality and stuff. And so the link between the two are these 5 properties in this theorem, this reconstruction theorem. So this is the part that I never hear about. So I would like to hear something about this. Would that be a reasonable plan for you, Chul, or you're not ready to talk about that? I mean, the way you described everything up to now was very nice.
So you'd like to know more about the reconstruction theorem equivalence between the Euclidean and the Minkowski theories?
Yeah, under these assumptions. Yeah, I mean, sort of, just in a vague way. Not. I want to get the intuitive ideas.
Yes, I can. Yes, I can just summarize the famous paper published by the Osterwalder and Schrader, and give another talk next week.
Okay, wonderful. Is that okay, Vincent?
Sounds great to me.
Okay, so you be in charge, because I'm going to be on the road, and I hope my iPad will connect in. Okay.
All right. Yeah, that's no problem.
If you guys are lucky, I
I'll
won't be
take care
able
of
to
it.
connect in and be shouting into the phone all the time.
I have a final question here that
All right. Go ahead. Yeah.
that the phi-4 theory that I've heard about, that the quantum mechanics talk about, that it's because it has instanton and soliton solutions. In Navier-Stokes, when you try to do it in the Navier-Stokes equation, what would correspond physically to those instanton, soliton solutions? What would you expect to find?
I am under the impression that phi-4 theory is not directly related to the Navier-Stokes equations. Does this answer your question?
No, well, he wanted to know if Navier-Stokes would have something phenomenon in it that would be like that the words instantons or solitons could be attached to.
I have not really thought about that yet, so I am not able to give a sufficient answer right now.
Dennis, the related O3 symmetry groups have all kinds of interesting topology with the projective plane and so on. And if you take the real version of the O3 symmetry group, SO3, you get elasticity equations. So there's all kinds of things that come out of this line of reasoning, but not exactly Navier-Stokes.
Okay. Yeah, I remember when Arthur Jaffe came into the back in the 70s at IHES, he came into the cafeteria and he was talking about these metrics on the two-sphere which develop conical singularity points, and then they had a moduli space, and they were called monopoles or something like that. And they satisfied the monopole equation. And that's in the language of. So that's sort of in your dimensions 2 and 3, and sort of also in this discussion of instantons. Okay, so next week we'll hear some more about the foundational matters related to going from the Euclidean signature back to the realistic Lorentz signature. Is that right, Minchu?
Yes.
Okay. So thank you for being so diligent.
Minchu, I know you answered slightly the question in chat, but when you have this Lagrangian and you know, are you planning on getting Feynman diagrams or, deriving Feynman rules from the Lagrangian? And when you do that, is there anything, I know in some theories, there's a lot of relationship between the topology of the Feynman diagrams and sort of the ultimate calculations that you do. So I'm wondering here, is there some sort of, interesting thing one can say by reading off of Feynman
floating around? We're not exactly sure how to use them, but we have those technologies and we're developing them.
That's exciting. Yeah. So then maybe you could say something about Navier-Stokes by looking at the Feynman diagrams that you derive from the.
Well, we don't have conclusions yet, so I can't say anything.
Okay. Okay. Yeah, no, that's awesome. Okay. Thank you. Yeah. Thank you.
Oh, Dennis? Regarding the recording, whenever it's uploaded, just send me the link and I can share it with the group.
Okay, well, edit out some of my screaming, okay, with Sasha.
I'll have to look into that. Yeah.
I'm Irish. I get mad, blow my stack, and then I'm totally friendly again. I don't hold any grudges. I get it all out. Okay.
Right.
I keep telling that to my wife. Hope this is not recorded. Anyway, edit that out too. Okay, I will do that.
I'll see what I can do. Yeah.
Okay, fine.
And Asil also asked, would you be willing to share slides, Mitchell? And I suppose I'll ask James too, since
Okay.
Uh,
Where do I upload the slides?
You can just send them to me and I'll just send them out to the group when I get the link to the recording from Dennis.
Okay.
Okay, so.
Thank you very much.
Okay,
Yeah.
thank you, everybody.
Thanks,
Good
everybody.
stuff. Thank you.
Take care. Bye.
Take care.